All right, so welcome to Math 140 Calculus 2. I will be sending you an email later today about the upcoming lectures. I will have Monday's lecture a more accessible talk because we have the possibility of prospective students coming. So if any of you have prospective students who are visiting and trying to look for something to come to, the class will be accessible to them. It would be great if they've done at least Calc 1, not necessarily Calc 2, but if they haven't done calculus, it will still be accessible. Okay, what I want to do today is I want to continue talking about sequences and series. This is one of the big themes depending on who is teaching the class. And given how important this is for a lot of later scientific stuff, I really want to make sure we cover that in this course. Whenever you see infinities in mathematics, this is the danger zone. And you have to be careful, you have to be able to justify that everything works out nicely. So just because you add infinitely many things doesn't mean you're going to have a sum that converges or is meaningful. And that's what all of this stuff is for, is when can we say this infinite sum converges to something we can work with? Why is this useful? Well, a lot of functions are defined by infinite sums. The exponential function, and related to the exponential function, the sines and the cosines. These are some of our go-to standard functions to model the world. So we need to understand how these behave. We need to understand how do you find these values. So we'll talk a little bit more about convergence tests for series. We'll talk about the ratio test, the integral test. We might get to the root test today, maybe the alternating and non-increasing and absolute value test. So last time we talked about the sum n goes from 1 to infinity of 1 over n squared. And we wrote this as a sum k goes from 0 to infinity of 1 over 2 to the k squared plus 1 over 2 to the k plus 1 squared plus dot 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 1 over 2 to the k plus 1 minus 1 squared. And what we did is we just broke this up. This is called like a dyadic decomposition. We break it up into blocks where each block is twice as long as the previous. So a block of like 1, then 2, then 4, then 8. And what was nice is in all of this stuff here, it's at least 1 over 2 to the k plus 1 squared, and it's at most 1 over 2 to the k squared. Well, this is just 1/4 times 1 over 2 to the k squared. So the difference for all of the terms between the smallest and the largest in each of these blocks is at most a factor of 4. So we can get a lower bound by replacing every sum in the parentheses with the smallest. We can get an upper bound by replacing every sum with the largest. So if we want to show that it converges, we just replace everything with the largest. And that will give us a good upper bound. If we then did the lower bound, we would then say, oh, the true answer lies somewhere within this factor of 4. And so this sum, n goes from 1 to infinity of 1 over n squared, is going to be less than equal to the sum k goes from 0 to infinity. How many terms are there? Well, we go from 2 to the k to 2 to the k plus 1 minus 1. So we basically have 2 to the k terms, and each term is at most 1 over 2 to the k squared. So now we have to remember rules of exponents. What's 1 over 2k? What's 2k squared? 2 to the 2k. So this is equal to the sum, k goes from 0 to infinity, of 2 to the k over 2 to the 2k. This is the sum, k goes from 0 to infinity, of 1 over 2 to the k, which is the sum, k goes from 0 to infinity, of 1/2 to the k. So by the geometric series formula, it's 1 over 1 minus 1/2, it converges. So not only do we know that it converges, but we even have a rough idea of what it converges to. And it's at least 1/4 of this. This is actually known as the Basel problem. It's very famous. The answer is pi squared over 6. Whenever you see a pi squared, you know something interesting is happening. There's a lot of fun stuff that's related to this. The fact that this is pi squared over 6 actually implies that there are infinitely many pi's. So there's a lot of really interesting stuff going on. We had to be a little bit clever when we were doing this. We broke it up into blocks where each block was twice as big as the previous, And in each block, we said, what's the largest it could be? What's the smallest it could be? And then we use that to get a sense of the true value. I think this is a bit of a hard proof. Now, we are taking a calculus class. What should you know if you're taking a calculus class? What material should we have available? What should be available to us? Algebra, because that's a prerequisite. But what else do we know in a calculus class? What can we do? We can take derivatives and take integrals. Where have we seen sums related to either a derivative or an integral? We've seen sums before related to one of them. Integrals, the Riemann sums. And in fact, this is actually equal to zeta of 2, where zeta is the Riemann zeta function. So this is a really big day for Riemann. So we've seen Riemann sums, and the idea of a Riemann sum is we have our function, and we chop the interval from, say, 0 to 1 into lots of pieces. And then in each one of these, maybe I'll just do, the left endpoint. We find the areas of the boxes, and we use that to estimate the area under the curve. And in the limit, as the thickness goes to 0, it's going to converge to the area under the curve. And then calculus kicks in with the fundamental theorem of calculus, which says that if this is the curve y equals f of x, and big F prime equals little f, then the integral from 0 to 1 of f of x dx, which is the area, is going to be f of 1 minus f of 0. So we have a way to calculate this. It turns out we can use this to get a test on whether or not a series converges or diverges. But it has to be a special series. So assume the sequence AN is either non-increasing or non-decreasing. So what does non-increasing mean? So what does it mean if you're non-increasing? So what does that mean between, say, AN and AN plus 1? So what must be the relationship if you're not increasing? Okay, so given that I'm writing AN and AN plus 1 here, how would you write it? AN has what relation to AN plus 1? Is greater than or equal to. So we have to remember the equal to. Non-increasing is not the same as decreasing. You could allow yourself to have the same value. If we're non-decreasing, that would mean AN is less equal to AN plus 1. So it turns out if you have a sequence of terms that's non-increasing or non-decreasing, we can often use calculus to find out whether or not it converges. And the idea is the following. Let's take a very nice one. Let's take AN equals 1 over n. So here's 1, 2, 3, n plus 1. Okay. Now, at 1, it's going to be 1. At 2, it's going to be 1/2. At 3, it's going to be 1/3. All the way down to n, it's going to be 1 over n. Okay? We have two ways of doing things. I'm going to do things mostly rigorously. I'm not going to worry too much about the left and the right endpoints. I want to do just enough detail so that you understand how to do the test. If you want me to do more detail, I am a pure mathematician. I live for questions like that. If, however, I've done enough that you're comfortable, I'm quite happy to leave it like that and resist my temptation to be very, very theoretical. Right? So let's just look at what's going on. I want to calculate the sum, say, m goes from 1 to n of 1 over m. I'm going to write that as the sum, m goes from 1 to n of 1 over m times 1. Can I just multiply all the terms by 1? Is that legal? Yeah. I can add 0 and I can multiply by 1. It's a great day when you get to do both. It's a good day when you get to do at least one of them. Why do you think I want to multiply by 1? So what would 1 over m times 1 represent? Can you give me a geometric quantity that might be represented by 1 over m times 1? Think back to what we were doing with Riemann Sum, breaking things up. How might you view 1 over m times 1?
Value.
Yeah. So if I go from 1 to 2, that's going to have a length of 1. And here's my box. So this area is 1 over 1 times 1. The next one has area 1/2 times 1. And so on and so on. So now I want to find a function that looks a lot like 1 over m. So we have our sequence am. I want a function f of x such that f of m equals am is 1 over m. Can you give me a function of x such that whenever you take x to be m, you get 1 over m? Yes. Take f of x equals 1 over x. Usually just replace the index with x. That almost always works. Whatever the index is, make that x. Instead of 1 over m, we have 1 over x. If I had 1 over m squared, what would you take your function to be? 1 over x squared. And so if you look at what we have now, so here's the function f of x equals 1 over x. And do you see how the area of the boxes is a little bit larger than the area under the curve? Now, I drew my box going from 1 to 2. What's the other way I could have drawn the box? 2 to 1, and then the first box would have gone from 1 to 0. So if I draw it the other way, then the function is going to have a larger area than the area under the boxes, except for the fact that I don't have the first box anymore. So for this problem, I would have now the area under the function is now greater than the area under the boxes if I remember to add on that little extra term. So I would have, so let's do the first one. If I integrate from 1 to n of 1 over x dx, okay, that's the area under the function. Do we agree that this is going to be less than or equal to the sum, m goes from 1 to n of 1 over n? Because over here, I'm looking at the stuff going to the right, so that's always going to be a little bit larger. Now, if I look the other way, it's going to be the sum, m goes from 1 to n of 1 over n minus the first term. Because when I'm looking at what's going to the left, the area under my curve is greater than everything, but I didn't include that first box. So I have to remove that from my sum. So is everybody comfortable with this?
I'm still looking at that.
Well, because if you look at what's going on to the left, see this first box over here? We're not looking at the area under the function from 0 to 1. We're only integrating from 1 to n. So from 1 to n, the area under the function is larger than the box with 1/2. It's larger than the box with 1/3. It's larger than the box with 1/4. But we didn't include that. We didn't include that first box. That's why we have to subtract it.
Okay. And it's 1 because the area of that box is 1.
Correct.
Okay. Right.
Yeah, because the height is 1. So instead of writing it as 1, I could actually write it in a better way as 1 over 1. So what we're essentially telling us here is that the difference between the integral and the sum is just is at most the first term. Wow, that allows us to evaluate things really accurately. What you could do is you could evaluate the first 10 terms by hand, and then start with the 11th term, and then use the integral to evaluate the sum from the 11th term. So we can get extremely accurate results. So this is the integral test. Any questions about the integral test? So now let's actually compute it. So we have, 1 plus 1/2 plus ... plus 1 over n minus 1 is thus equal to the integral from 1 to n of 1 over x dx is thus equal to 1 plus 1/2 plus 1 over n. So again, the difference between the left and the right-hand side is at most 1. So this integral is potentially very close. All right, what is the integral equal? What function has derivative 1 over x? ln of x. So the natural log of x, and we evaluate it 1 and n. What's the natural log of 1? 0. So this is equal to the natural log of n. So 1 plus 1/2 plus ... plus 1 over n is within 1 of the natural log of n. As n gets very, very large, what does the natural log of n go to? Goes to infinity. So anybody know how Elon Musk made the news this week? How did he make the news? He bought more than just shares of Twitter. He bought a tremendous amount of shares of Twitter. He bought like 9%. His purchase stake was in the billions. Okay, imagine now all of a sudden his accountant says, Elon, or actually Mr. Musk, there was a mistake. The amount I told you was a little bit off. You actually owe $1 more for your new stake in Twitter. Musk's response would be, having me respond to this is such a waste of my time. In terms of just how much that dollar is worth. Is the dollar noticeable at all when we're talking about something on the order of billions of dollars? Absolutely not. So when this is going off to infinity, being off by 1 is negligible. This is not a big problem at all. This is a remarkable success. And we saw something like this when we were looking at the harmonic series, when we kept grouping things in groups of 2. Every time we did 2 terms, then 4, then 8, then 16, then 32. Every time we did that, we added another half. And we saw that the size is on the order of the log of the number of terms. And that's what we're getting over here right now. And we're now just proving this rigorously. We're within 1 unit. That's really good. Let's do another problem. Let's do 1 plus 1/2 plus ... plus 1 plus 1 over 2 squared plus all the way up to 1 over n squared minus 1. Let's equal to the integral from 1 to n of 1 over x squared dx is thus equal to 1 plus 1 over 2 squared plus ... plus 1 over n squared. So is everybody comfortable that we still have a sequence that's non-increasing? This is in fact a sequence that's decreasing. And we can approximate it with this integral. All right, what function has derivative 1 over x squared? Plus 0. And if it's easier, we can write this as x to the negative 2 dx. So what function has derivative x to the negative 2? Plus 0. Yep. So I always like to first fix the exponent. I know I have to increase the exponent by 1. And now when I take the derivative, negative 1 comes down. I want to have just a plus 1. So I know it has to be negative 1. So this is just going to be negative x inverse at 1 and n. I could evaluate it directly, but I just want to just remind everybody that if you have a negative sign in front of it, that's the same as flipping the order in which you evaluate. So this is the same as x to the negative 1 at 1 and n. And I'll just do it both ways. So here, I would get negative 1 over n minus negative 1 over 1, or 1 over 1 minus 1 over n. Which algebra do you prefer to? The first or the second? Second. You know, I hate having negatives of negatives, and you're worrying about whether or not I'm going to drop something. So if I have a situation like this, I like to just flip the bounds of integration. And so both of them give us 1 minus 1 over n. So we know the sum converges and is within 1 unit of 1 minus 1 over n. So as n goes to infinity, the sum of 1 over n squared equals 1 plus an error at most 1. Now, over here, were we happy to be within 1 unit of the natural log of n? You know, when n is really large, are you being within 1 unit, are you happy? Yes. If you tell Mr. Musk that he owes $1 more for his 9% stake in Twitter, not a big deal. What about over here? What if I tell you you're within 1 and the sum is equal to 1, plus or minus an error of size at most 1? So the sum is somewhere between 0 and 2. How happy are you? You don't seem as happy. It's tough to tell with the masks, but the eyes, I think you're giving it away. Why aren't you happy? Yeah, the error is as big as you're off by at most 100%. Now the other thing is, when you look at the sum 1 plus a fourth plus a ninth, what can you tell me about the value of the sum? Can you give me any easy balance for this infinite sum? It's at least 1. The first term is 1. If you take the first 2 terms, it's at least 1.25. So when I tell you it's 1 plus or minus an error of at most 1, well, I know I'm already off by at least 25%. So the error is actually quite large here. So you can see that for things that converge, the error might be really bad. What you should do is do 1 plus 1 over 2 squared plus, say, 1 over big N squared plus 1 over n plus 1 squared plus ... And do this by hand or computer. And then this is going to be basically of size integral from n plus 1 to infinity, 1 over x squared dx plus an error at most of size 1 over n plus 1 squared. And we're off by at most the first term. Well, now because I'm starting at n plus 1, if n plus 1 is huge, now my error is going to be small. So if I need to evaluate this very precisely, what I do is I do a bunch of terms just directly by brute force. And then I know, okay, now if I just start from this point onward, I know my error won't be too bad. And this integral over here is going to be 1 over n plus 1.
Yeah, I get the error.
So for a lot of things, yes. And when we get into a lot of advanced mathematics, if you are very lucky, you have an infinite sum, and this occurs in a lot of the work that I do, and the first term is 1, and all the other terms tend to 0 very, very rapidly. And so that you can ignore them, and it then just becomes a game of just how quickly can you ignore them? How insignificant are they? So this is the integral test. So if I now give you the sum n goes from 1 to infinity of 1 over n to the p, where p is greater than 0, can somebody give me what function I should use for this? What should f of x be? So what function should I take? 1 over x to the p, or x to the negative p. And then when you do the calculation, if p is greater than 1, it converges. If p is less equal to 1, it diverges. If p equals 1, you have to use the natural log. So you have to, the integral is a little bit different when you're finding the antiderivative. If p equals 1, you have 1 over x. The antiderivative of 1 over x is the natural log of x. If p is less than 1, like 1/2. But of course, to some extent, as soon as you know it converges for one value of p, it converges for all larger values. As soon as you know it diverges for value of p, you know it diverges for all smaller values. So once we know it diverges for p equals 1, it diverges for everything small by the comparison test. As diverges for p equals 1, diverges for all p less than 1 by the comparison test. Okay, so now we have a lot more examples of sequences in series that converge or diverge. So we had the geometric, and now to that we can add p series. Why do you think it's called a p series? There's a p. Why do you think they use p? I have no idea. I'm just guessing right now by my mastery of the English language. What do you think p might stand for? You think of any words that begin with a p that might be appropriate here. I'm sorry? Not probability. We're raising n to a power. So I think p is power. We're looking at power series. Okay. So the next, have we talked about the comparison test? All right, so if I have 0 less equal to an less equal to bn, and the sum of bn and goes from 1 to infinity converges, so does the sum and goes from 1 to infinity of an. And if I have 0 less equal to cn less equal to an, and the sum and goes from 1 to infinity of cn diverges, so does the sum and goes from 1 to infinity of an. So this is sometimes called the sandwich theorem. In the first case, each an is non-negative, and it's less than bn, and the sum of the bn's is finite. So the sum of the an's have to be finite. If your sum converges, what do the bn's have to go to? So this is a necessary condition. If your series converges, what must the terms be going to? 0. So if the bn's are going to 0, I'm just sure. It's just the school saying my daughter is not there, even though we called the school and emailed the school. And yes, this is now being recorded. Automated systems. So Bn is going to 0, so an has to be going to 0. And because the sum of the bn converges, if you go sufficiently deep down in the b's, quadrillionth term down, a googolplex down, and sum from that point onward, it's going to be extremely small. Therefore, the sum of the an's from that point onward must also be small. So another way to look at it is, I start off at some height, and because the an's are non-negative, I'm only adding to it. I'm only going up and up and up and up. And I can't go up beyond a certain point because I know the sum of the n's converge, so I have to converge. To prove this rigorously, you really want to use some ideas from real analysis. If people want, I am happy to go into that level of detail. I think for a first course, a first introduction, I'm hoping that this falls under the blatantly obvious. If the bn's converge and I'm non-negative. Now, is the non-negative needed? What if I drop the non-negative? Well, we'll do that in a second. So the other one is if the CNs diverge and the ANs are larger term by term, then clearly some of the ANs will blow up. Oops. What if we just had AN less than equal to BN and the sum of BN converges? Does the sum of the ANs have to converge? So for example, let's say I want AN less than equal to 1/2 to the n. Can somebody give me a sequence of ANs where each one is less than 1/2 to the n, but the sum won't converge? Let's look. What was the initial condition? Yeah, so if you look at it, I'm assuming 0 is less than equal to AN is less than the n. So probably something with a negative would be a way to go. So what's the simplest sequence you can think of involving negatives? AN equals -1 every single time, -1. If AN equals -1, the -1 is always less than 1/2 to the n, but the sum n goes from 1 to infinity of -1 diverges. And this shows us that the condition was necessary. So one of the habits you should get into is whenever you're doing math, really know what are the conditions on the theorems that you're using and make sure that you check to see if they're true. Years ago, when I was a postdoc, a graduate student showed me their dissertation, and I had a little fun with it. I looked at it, and about a minute or so, they said, I really like this result. This is similar to work that I do. By the way, do you know that half of your thesis is wrong? I just knew the look of horror on his face when I told him that half of his thesis was wrong. I said, what? Now, the reason I knew half of his thesis was wrong is he was citing a paper that I know very well, and the paper says very clearly in the introduction, henceforth we assume K is 2 more than a multiple of 4. So it's either 2, 6, 10, etc. If K is a multiple of 4, then there's an extra negative sign that comes in. So it takes less than 30 seconds to fix this thesis. You just have to say when K is a multiple of 4, you have to put in an extra negative sign. But what was going on is he was looking at a paper and he just looked at the statement of the theorem. And this was not well written. I always like to reproduce all the assumptions before stating a theorem because people sometimes don't remember to check everything beforehand. And so his thesis was easily fixed, but he had a heart attack and he learned, I think, never to do this again, to always be very careful, read everything in the paper up to the point that you're quoting to make sure you know what's being assumed. Usually, if you drop an assumption, the result is false. Usually these assumptions are here for a reason. So if you're trying to understand the theorem, say, well, what would happen if these assumptions are false? So let's do the other one. What if Cn is less than equal to An and the sum of Cn diverges? Must the sum of An diverge? So what condition have I dropped here? Yeah, so what would you want to take for Cn for a sequence that diverges?
We do -1 here.
Yeah, let's do -1. Eventually you start to have your go-to sequences. Let me try something simple. Let me just try -1 every single time. If that doesn't work, let me try -1 over n. Or maybe -1 over n squared. Or -1/2 to the. So you try a bunch of different things. And then what should we take a and to b? We want something that converges and is always greater than or equal to -1. 1 over n squared. So we have, -1 is less than or equal to 1 over n squared, but the sum of 1 over n squared converges. So this tells us that our assumption that it was non-negative is very, very important. These results fail when we have a situation where the terms are not negative, the terms are not forced to be non-negative. Okay. Any questions on the statement of the comparison test? So let's consider the sum n goes from 1 to infinity of n squared over 3 to the n. So do you think this converges or diverges? So you can make an argument for both converging and diverging. What makes you think it might converge? There's got to be something good about this function. Yep. Well, which thing looks really good as n gets large in terms of convergence? Which makes you, the 3 to the n makes you feel very comfortable that you should have some convergence. What makes you a little bit worried that it might not converge? The n squared. So we basically have a battle of n squared versus 3 to the n. Who's larger, n squared or 3 to the n? So I claim n squared is less than or equal to 2 to the n. Okay. If true, then n squared over 3 to the n is going to be less than or equal to 2 to the n over 3 to the n, which is 2/3 to the n. And what do we know about the sum n goes from 1 to infinity of 2/3 to the n? This converges. Why? Okay, but why do we know 2/3 to the n converge? 2/3 to the n converges because this is one of our big friends. It's geometric. It's a geometric series with r equals 2/3. So all we have to do is show that n squared is less than or equal to 2 to the n. And this is where it becomes an art. Okay. So as much as possible, we want to, and it sounds painful to say this, we want to reduce math to not having to think. It's just, I put things in a crank and I solve it. So art versus just a crank. If I give you x squared minus 7x plus 12 equals 0, what are the roots? So how would you solve x squared minus 7x plus 12 equals 0? Okay, and what are the factors? Yeah, so I know it's either 112, 26, or 34. Because it's a plus 12, it's either both plus signs or both minus signs. But because it's a -7, it has to be both minus. So it's got to be something like x minus. So I want two things that add to 7 and multiply to 12. It's 3 and 4. Whoa. All right. So that finishes the class. I'm going to just actually go back and just quickly redo the last few minutes because it did not record. So we did this part. And did we do this part before the video stopped projecting? Okay. So I'm going to just record right now. So apologies for doing this again. You feel free to leave. We had some technical issues. So we talked about doing things as an art versus a crank. So if we have x squared minus 7x plus 12 equals 0, we could try to solve this by factoring. And we noticed that 12 is 1 times 12, 2 times 6, or 3 times 4. Because it's a plus 12, it's either 2 positive signs or 2 negative signs. Because we have a minus 7, it's got to be 2 negative signs. We get x minus 3, x minus 4. If I gave you instead x squared minus 7x plus 11, unfortunately, there's no easy way to see the roots. So we have to use the quadratic formula. We want to show that n squared is less than or equal to 2 to the n if n is big. So one thing is we can look at n squared over 2 to the n, and we can basically use L'Hopital's rule. You know you've made it if you are a verb. And so if we do L'Hopital once, we get 2n over e to the n log 2 times log 2. Do it again, we get 2 over e to the n log 2 over log 2 squared. We no longer have infinity over infinity. We can't do L'Hopital anymore. We see that this is 0. So since this is 0, this means n squared over 2 to the n goes to 0. So n squared times 2 to the n times 2 to the n, I've just multiplied by 1 again. This is still just n squared. So n squared over 2 to the n goes to 0. Eventually, it's at most 1/2. So this is going to be less than or equal to 1/2 times 2 to the n when n is large. And that's enough to prove that n squared is less than or equal to 2 to the n. Here's another way to prove that n squared is less than 2 to the n for n big. We can write 2 as 1 plus 1. So 2 to the n is 1 plus 1 to the n. It's 1 to the n plus n choose 2 plus so on and so on and so on. So which term is going to give us the domination over n squared? Well, we get 1 plus n minus 1 over 2 factorial, and n minus 1 and minus 2 over 3 factorial, and so on. 1 is not enough to beat n squared. N is not enough to beat n squared. The n squared minus n over 2 is not enough, but the next term looks like approximately n cubed minus something n squared over 6. So when n is really, really large, this term is at least n cubed over 2,000, which will beat the n squared. And so this is another way to show that n squared is less than or equal to 2 to the n. What if I give you n squared over 3 to the n? Well, if I give you n squared over 3 to the n, we can just do a comparison test, and we will see that if we just drop the n cubed, what we've done is we've made the denominators smaller. If we make the denominators smaller, this makes the fraction larger, and so by the comparison test, we're okay, and we know that this will converge. A slightly harder one is if I give you n squared over 3 to the n minus n. And so now the problem is we have a negative in the denominator, and so if I just drop the minus n, I've actually made the denominators smaller, which make the fractions larger. So we need to prove 3 to the n minus n has some nice saving graces. With a little bit of work, you can show that it's at least 1/2 3 to the n. There's lots of different things you can try to do. All right, have a great rest of the day.